Okay, we're going to work through the 0.1 algebra skills review. The first one says to expand the expression x plus h cubed, and the suggestion is to try to use the expansion of a square of a binomial to help. So as a little refresher, square of a binomial is if we have a plus b squared, this will expand to a squared plus 2ab plus b squared. That's really handy to have memorized because expanding a binomial like that, a binomial square, is just really common to have to do. So if we come over here, x plus h cubed could be written as x plus h squared times x plus h. Using the expansion of the square of a binomial, I would get x squared plus 2xh plus h squared all times x plus h. And now if you want to confirm that x plus h squared results in this, you could always just do out x plus h, and then you could FOIL, distribute, use the box method. You could do x plus h, and no matter what, you're still going to get x squared plus 2xh plus h squared. Okay, so I highly recommend just sort of knowing the square of a binomial, being able to recognize it, saves time, and is really handy. Okay, now to multiply this trinomial by this binomial, we'll just use the distributive property. Everything from the first, needs to get multiplied by everything from the second. So the first three terms get multiplied by x, giving me x cubed plus 2x squared h plus h squared x. Then I multiply everything by the second term of the second one. So x squared times h gives me plus x squared h. 2xh times h gives me plus 2xh squared. And h squared times h gives me plus h cubed. Looking to combine like terms here, I don't have another x cubed term, so I have x cubed. I can take 2x squared h plus this 1x squared h, giving me 3x squared h. Then I have h squared x plus 2xh squared, which could also be written as h squared x. So one of those plus two of those. I'm going to choose to write this as plus 3xh squareds. And then we have h cubed with nothing to combine with. Okay, so we get our full expansion here. And if you've learned or can recall from Pascal's triangle, we have the coefficients. So the triangle looks like 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so on. Where each next row comes from the sum of the terms before it. So 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, 3 plus 3 is 6, so on and so forth. And that Pascal's triangle here, Pascal's triangle, allows us to do binomial expansions. So the first one would be x plus, we'll say h to the 0, just gives us 1. The next one would allow us to do x plus h to the first, which would just give us 1x plus 1h. Then x plus h squared, the square of a binomial, gives us 1x squared plus 2, and maybe I'll put this over to the side, 1x squared plus 2xh plus 1h squared. This one was just 1x plus 1h, or x plus h, and this is just 1. And you'll see that that's exactly the same as just the general square of a binomial. And then the 1, 3, 3, 1, well, we'll notice we have a coefficient of 1, 3, 3, and 1. And in addition to those coefficients, we also can see the exponents go from x cubed to x squared to x to the first. And then in the last one, it would be like x to the 0. There is no 0, it's just multiplying by 1. On the other hand, we go from h to the 0, or we don't see an h here, then h to the first, h squared, h cubed. So the power of one variable is decreasing. The x power is going from 3 to 2 to 1 to 0, compared to the h power is going from 0 to 1 to 2 to 3. Okay. Notice that the sum is always 3. So x cubed and then h to the 0 here, which is just 1, would give us an exponent of 3. X squared, h to the first, if we add those 2 plus 1, gives us a total exponent of 3. So it's kind of handy to see that pattern, refresh it, and and that'll help us in the next problem. So if we want to expand the expression x squared minus 3 cubed, so that's the cube of a binomial, where our binomial is made up by x squared and minus 3. Okay, so those are the two components of our binomial. Now the x squared is sort of like that first term, the x or the a or whatever you want to call it. It's the first part of your binomial. And then the second part is kind of like the h. But usually we think of it as x plus h or a plus b squared, and we expand it. So if you have minus 3, let's just consider this as plus negative 3. So in this case, our h value is negative 3. And so we could do this all out. We could do it the same way. We could do the square of a binomial. But if we want to try to use our answer from question 1 and look for structure, this right here is going to allow us to expand it. Because we're saying the x in this example, x is now x squared. And the h is now negative 3. So what we're going to do is just replace it. So if I have 1x cubed as my first term, 1x cubed, well, x is now x squared. So instead of x, I should say 1x squared cubed, which we know is x to the 6th. Now my next term has a coefficient of 3 that relates back to Pascal's, as well as we can see it when we expanded out our x plus h from before. So plus 3 x squared, but remember x is now x squared, so it's x squared squared, replacing this x with x squared, times h to the first, but h is now negative 3, so times negative 3 to the first power. Okay, well, 3 times negative 3 is negative 9. X squared squared is x to the 4th. Then we go to our next term, plus 3 x to the first. So x to the first, but remember, it's x squared, and then that to the first, because x is now x squared. And then h squared, but h is negative 3, so times negative 3 squared. Negative 3 squared is going to give us 9, and 9 times this 3 is going to give us 27. So we get plus 27. X squared to the first is just x squared. And our last term was 1h cubed. So plus, but instead of h, remember we have negative 3 cubed. Negative 3 times negative 3 is positive 9, times negative 3 is negative 27. So minus 27. And if we box all this up, that is our answer. So we completely use the structure that we found with this general example of x plus h cubed. And then we use the different value of x. We substituted an x squared here, here, here. And a different value for h. We use negative 3 here, here, and here. And we filled that into our structure, and we were able to do this in a different way. Okay, so we're going to move on to number 3. It says simplify 3x plus 2y over 3x plus y if possible. If not possible, state why. So we have 3x plus 2y over 3x plus 1y. We actually can't simplify that. We can't really do anything and cancel it. It might be tempting to say, oh, we have 3x and 3x, let's cancel that. And then 2y and 1y, maybe we turn it into 2 over 1. Oh, yay, but not yay. Not yay. Because you can only cancel common factors. Okay, oops, we're back. Okay, can only cancel common factors of all terms. Okay, so I can't cancel anything that's not a common factor of everything. I can't cancel the 3x. I can't cancel the y. I can't cancel the x. Can't do anything like that. If, for example, we had maybe like 3x plus 2y over 6x plus 4y, well, then I could factor out a 2 here, and then I could say 3x plus 2y over 2, 3x plus 2y. now there's a common factor of 3x plus 2y, and I would get 1 over 2. But generally, when there's a plus sign here, you really want to make sure that we actually have common factors. You certainly can't just cancel out things that are being added without considering what else is happening. So make sure to be careful for that. That's a really, really common mistake. So look out for that. Similarly, if we look at example number 4 here, simplify if possible. Again, for the same reason, not possible. No common factors of all terms. And terms are chained together by addition. So 3x plus 2y, 3x is a term, 2y is a term, 3y on the bottom, 3y is a term. Okay, terms are separated by addition or subtraction, I guess. And so there's no common factors there. These two terms have y and y, but this term does not. These two terms have a 3 and a 3, but this term does not. So there's no common factor that can cancel out of everything. Yeah, so there are no common factors of all of the terms. Okay, on to number 5. It says simplify 5x plus h cubed minus 5x cubed all over h. So that is going to be a pain if we just do out this whole thing. However, in question 1, we literally did x plus h cubed. We got this whole expansion of it. It related back to this row of Pascal's triangle, x plus h cubed. And so we're just going to use that. So if I have 5, and if my expansion of x plus h cubed was x cubed plus 3x squared h plus 3xh squared plus h cubed minus 5x cubed all over h. Okay, that's great. Because we use that structure, we use Pascal's, we make that expansion a little easier. Then we can distribute in this 5, because we'd like to see if we can combine some things in the numerator, end up with some common factors. So I'm going to get 5x cubed plus 15x squared h plus 3xh squared plus 5h cubed minus 5x cubed all over h. If we look at the numerator, here's a term, term 1, term 2, term 3, term 4, term 5. The denominator, we have one term. So remember, terms chained together by addition and subtraction. I'm looking for common factors of all terms, and then we can cancel those. Okay, so at the moment, there's not really a common factor of all the terms. In the numerator, there's mostly some 5s. Oh, at some point, hopefully you're not yelling at your screen because I did not actually distribute this. That is a 15. So the common factor of 5, but that doesn't really, I don't know, help us as much as we might want it to in the numerator, because it's not in the denominator. And yeah, you could factor it out of the numerator, but we just distributed it in. So like, I don't know. What does seem to be kind of common is this h, a bunch of h's. However, these two terms don't have it. But on the plus side for us, we have 5x cubed and minus 5x cubed. So 5x cubed minus 5x cubed is 0. So those cancel in the numerator, leaving us with 15x squared h plus 15xh squared plus 5h cubed all over h. Now we've got all these terms in the numerator with an h and the term in the denominator with an h. So now we can go ahead and cancel our common factor. And this kind of thing happens all the time in calculus, which is why it's sort of in this warm-up, where initially it like doesn't look like we could cancel h's, and even after this first step, but our x cubes end up canceling. Our 5x cubes cancel, leaving us with only h's, allowing us to cancel that h in the denominator. So when you get to calc, you'll see why that's more useful. But it's very nice. So we cancel, make it h to the 1, make it h squared. So our final answer would be 15x squared plus 15xh plus 5h squared. And we're happy. All right, on to number 6. Convert 3a over b plus b to a single fraction. So converting to a single fraction is as simple as needing a common denominator. And we usually use form of 1, foo, form of 1 to accomplish this. So if I have 3a over b plus b over 1, right, any number over 1, and I want the common denominator, the natural one would be just b, so I'll multiply by b over b, and I will get, do purple, 3a over b plus b squared over b. Now I can combine with that common denominator, and I get b squared plus 3a all over b. That 3 looks like a b, so let's do that a little better. Close it off, call it a day. Single fraction. So common denominator for single fractions, use a form of 1. Oftentimes it'll be more complicated, but this is the basic idea. So if we look at this next example, we have some nested radicals. Generally, if we have more than one radical happening, your steps 1 is get to general form. We have a in this problem, so I'm going to say b over c over d over e. Okay, I want one fraction divided by another fraction, because then I can think of it as that one fraction b over c divided by the next fraction d over e, and I can use the reciprocal, b over c times e over d. And then step 4, profit. Or realistically, we end up with b times e over c times d. So we're going to do exactly that. If we look at our first our problem, we can see we have a over 2x plus h minus a over 2x. That's our top piece that we're trying to get to b over c. Then we also have all over, let's use a different color, all over d over e. So we want a single fraction in the bottom. Right now it's just h, but let's call it h over 1, so we can just treat it as a fraction. Great, so I need to get my numerator to a single fraction. Remember, we just did that right as a single fraction. We said we need a common denominator, use a form of 1. So the natural way to make this a common denominator is to multiply this by 2x plus h over 2x plus h, and this term by 2x over 2x. And so what we will end up with is 2xa all over 2x plus h. And at the moment, I don't think it's going to do any good to distribute that, so I'm just going to leave it, minus 2xa plus ah all over 2x, 2x plus h, okay, all over h over 1. Great, so now I've accomplished step number 1. Yahoo! So now we can do step 2. Actually, I haven't accomplished step 1. I should make my, I take back my Yahoo. We'll save that for 1 second. So now I should combine my numerator into a single fraction. To be careful to realize that this whole thing's being subtracted. So this negative sign is going to distribute to each part of the numerator of that term. We'll end up with 2xa minus 2xa. So those will actually cancel. And then we'll end up with minus ah. So we'll end up with negative ah over 2x plus h, all over h over 1. Now I can Yahoo. Yahoo! But I'm going to convert quickly to this form because I'm running out of space. So now that I've got two fractions being divided, I'm going to times or multiply by 1 over h. And then that's going to give me, well, 1 times negative ah is still negative ah, all over 2x times 2x plus h times h. And oh, look, we have a common factor in the numerator and denominator. Even though there's 3 multiplications or 3 things being multiplied, this is still one term because you'll notice everything's being multiplied. There's no addition separating it. Even though there's an addition inside this multiplication, we still consider that denominator to be one term. Meaning that the term in the numerator and term in the denominator have a common factor of h, canceling it, giving us negative a over 2x times 2x plus h. And then we are happy. However, we did do a couple of things here. So in our initial fraction, there are a number of things. Like our domain here is x does not equal 0. H does not equal 0. And then we also don't want 2x plus h to equal 0. Because if this was 0, this was 0, or this was 0, we would end up dividing by 0. And we canceled out an h, we canceled out an, well, that's all we canceled, I guess. We still have x and h down there. So by canceling out that common factor of h here and here, I need to make sure I state h does not equal 0, okay? That's a little domain restriction I need to note in there. The other ones are still present, like I still have 2x, so I don't have to state x doesn't equal 0 because it's still evident. I still have 2x plus h, so I didn't lose that either. But h does not equal 0, I should state in, because otherwise this expression is not completely equivalent to this expression. Technically, our original domain restrictions, if I solve this, I can say 2x equals negative h, x equals negative h over 2. Well, that would be a problem. So x cannot equal negative h over 2, because if it did, then this whole denominator would be 0. And you should plug that in and check it if you want to see. And I should look at, if I solve for h equals negative 2x, that would also make that denominator 0. So I should say h does not equal negative 2x. So technically I have 4 domain problems initially. X can't be 0, h can't be 0, coming from here and here. And then this expression can't be 0, and it would be 0 if h was negative 2x, or if x was negative h over 2. Those stay present in our final answer. That's still implied here and here, but h does not equal 0. We lost when we canceled the h. We lost it. Very sad. But now we got it back. Put back. And we're happy. Delightful. All right, let's see. Moving on to number 8. So simplify. Again, this is the same idea. We want one fraction in the numerator and one fraction in the denominator. I used a and b, but those a and b's have nothing to do with the a and b there. So I could say x over y over w over z. I want one fraction first, right? So let's go for that. Numerator, I need a over b minus a over 1 times b over b, using my form of 1 to get a common denominator. Okay, there's my foo. Well, let's make our foo red. We did that before, so why not? Okay, we'll even say foo. Then we put our fraction bar here. In the denominator, we have blue, a over 1 plus a over b squared. But if I want to know the denominator, let's distribute that squared in, a squared over b squared. So my foo down low is going to be times b squared over b squared. Foo. Delightful. Continuing that on out, we are going to get a over b minus ab over b over ab squared plus a squared over b squared over b squared. And don't get that eager beaver tendency. Like we'd be like, oh, look, I can cancel my b's and cancel my b squareds. It's like, yeah, because you just multiplied in the b's and the b squareds. Like, yeah, you put that form of 1 in there. Don't go canceling the thing you just put in there all willy-nilly. We put it in there for a reason. Okay? Don't be willy-nilly. So what we can do is make this one fraction in the numerator. A minus ab all over b all over ab squared plus a squared all over b squared. So that accomplishes goal number 1. Then remember, the point of that is to do x over y divided by w over z, and then multiply the reciprocal x over y times z over w. So we'll go over here and do that. Actually, let's snake up. Use all this free space. Up we go. And we'll switch to a nice purple. All right, so we get a, and I'm actually going to factor out the a there. So a 1 minus b, right, because these have a common factor of a, over b, times, here I have a common factor of a also. And so it's going to be times b squared over a b squared plus a. Okay, so the reason we factor is because when we multiply all this together, like why don't we just look for the common factors that can cancel right now? Because we'll note this is all multiplication in the numerator and denominator. There's no adding or subtracting other than in these groupings, but those groupings are being multiplied themselves. So, yeah. Okay, so then we have an a and an a that canceled, and a b squared and a b. So we're left with, what color? Pink, equals, or yields, 1 minus b over b squared plus a. So that's probably pretty good. But that wouldn't be perfectly correct. That wouldn't be exactly the same as our original expression because we have to remember the domain restrictions. So on our original function, right here, we can see b cannot be 0 because then we'd be dividing by b. And that also occurs from down here. We can't have b 0. We also can't have this whole thing be 0. Well, we also can't have b squared be 0. But that kind of gets covered with b does not equal 0. But that whole thing down there, we can't have a plus a over b squared equals 0. Or we can't have this whole thing be 0, which means that b can't be 0 from the denominator, or the numerator can't be 0 either, because then this whole big denominator would be 0. So if we try to set that equal to 0 and solve, factoring, we would get a b squared plus a equals 0. We get a cannot equal 0, and also b squared plus a cannot equal 0. Solving for a or b squared, a does not equal negative b squared. And we'd also get b does not equal plus or minus square root of a. I don't know if that one totally checks out, and I don't care to find out, because we still have b squared minus a, or b squared plus a in our denominator. So like that one's not lost, and I don't need to put that in. We did lose somebody along the way, though, and that somebody is this a. There is no dividing by a. We also lost this b with one of our b's up top. So I do need to manually state the domain restriction. A does not equal 0, b does not equal 0. So I need to put that here. And I should have finished my thought earlier. A does not equal 0. B squared plus a does not equal 0. And in this one is contained that thing like a does not equal negative b squared. B squared does not equal negative a. Whatever. But we didn't lose that one, so we're happy here. Happy. Okie dokie. Number 9, simplify. So here we go. We love to cancel common factors. Like, oh, cancel this. Yeah, even though they don't match. But we have a minus sign. So this is a term chained to another term. Look, it even looks kind of like a chain. Ready? Chain. Right? Doesn't it look like that? Where these are all plus, maybe it's a minus, and those are your terms chained together. And then the denominator is one term. So if we want to be able to do this, we need to kind of combine things and then maybe factor. So I'm going to distribute this out. I'll give you a look at the box method. Why not? So if we wanted to do this, we could have x minus 1, 2x plus 1, giving us 2x squared, 1x minus 2x minus 1. So that would mean that distributes and turns into 2x squared, 1x and negative 2x is minus 1x minus 1. Still have, I'm going to distribute this negative now, minus x minus 3 all over. Denominator I'm going to leave factored because it's not really going to benefit me to turn that into a bunch of different terms. The numerator we turn into a bunch of different terms because then when we combine those, for example, negative 1 and negative 3 is negative 4. Negative 1x and negative x is negative 2x. 2x squared is 2x squared. Okay, now I can look to maybe factor that quadratic again and see if anything's common and cancels. Hopefully it does, because this would be a much more interesting problem if it does. Numerator I can factor out 2, might as well factor it out because it'll make my quadratic a little bit easier to deal with, leaving with x minus 2, 3x plus 1. X squared minus x minus 2 definitely factors. Multiplies to negative 2, adds to negative 1, would just be negative 2 and positive 1. So, moving our along, let's go up here. Try gray. Gray never gets any love. Could say 2. That's probably why gray never gets any love. X minus 2, x plus 1, all over x minus 2, 3x plus 1. So now we've got everything being multiplied, so we can cancel this common factor. So now we'll get 2x plus 1, 3x plus 1. Except that's not perfectly the same as this. We lost one element of our initial thing. So in our initial function, and pause the video if you want to think of why it's not correct completely at the moment. Okay, so in our initial function, the denominator, like, right, we cannot divide by 0. Divide by 0 is bad, sad. Okay, so if I have x equals 2, we would divide by 0. So x does not equal 2. And then here, if x were negative 1/3, we would have a problem. Here, that's still evident. Like, x does not equal negative 1/3. I can still see that by looking at my n's function. But what I can't see, because I lost it, because I canceled it, is this. Lost in yellow. See, it's hard to see. It's lost. Sad. But we're going to be happy because why don't we just say, oh, okay, so x does not equal 2. Now these functions are identical. I still have my x does not equal 1/3 from here. Here I have x does not equal 2 manually stated in as a domain restriction. Beautiful. So don't forget your domain restriction when canceling and simplifying rational expressions, functions, yada. And on to number 10. Here we go. Same theme here. We got x's, we got h's. We want one fraction in the numerator, one in the denominator. So I'm just going to run it from here. Why don't I note some domain restrictions too? So right here, h does not equal 0, or we would be divide by 0, which is bad, sad. Okay. X cannot be equal to 0, because that would make that 0. And then x plus h squared does not equal 0. And the only way that's going to be equal to 0 is if x is equal to negative h, or vice versa. So I'd say x does not equal negative h, or h does not equal negative x. Okay. I don't really need to state both of those because they're both contained in one equation, but whatever. Okay, denominator's taken care of. I'll remember that for later. Unbox it. All right, let's go here. 1 over x plus h squared minus 1 over x squared all over h over 1. Denominator's all good. Numerator, let's use some foo. Foos are red for some reason. X plus h squared over x plus h squared. And then here I can multiply by x squared over x squared. Yielding, in green, x squared minus x plus h squared all over x squared plus, oh, not plus, times, what is it not letting me touch? Times x plus h squared all over h over 1. Okay, I'd like to turn this into some other fraction. Not some other fraction. I'd like to multiply by the reciprocal. However, I'm noticing this has got to try to combine. X squared and this, right? Those are two terms chained together by a minus. So I'm going to expand x plus h squared. It's the square of a binomial. Saves me the time and brain power. So I get x squared minus x squared plus 2xh plus h squared all over x squared x plus h squared. And I'm going to go ahead and multiply the reciprocal times 1 over h. Just get that going. Okay. Distributing in my negative sign, 1, 2, 3, I'm going to get x squared minus x squared cancels, minus 2xh plus h squared times 1, so that doesn't really matter. And it's not plus h squared. Classic mistake, Mr. Miller. That negative distributed to the h squared, so it's minus h squared all over. And then our denominator, I have x squared, x plus h squared times h. Beautiful. In the numerator, I have a common factor of h. I could cancel it right now if I'm clever. If I wanted to be really safe, I could factor it out first, so I could be like h negative 2x minus h all over x squared, x plus h squared times h. Great. Either way, I'm canceling my common factor of h, leaving me with my final answer. Yeah, let's go in the other direction. Negative 2x minus h all over x squared, x plus h squared. And I would be almost happy. So close. However, we lost something. Okay? We lost this. We lost our h's. Lost. It's yellow. It's hard to see. We're sad. Right? Remember, h did not equal 0. But when we canceled this common factor of h, we lost that h does not equal 0. Now in this answer here, if h is 0, whatever, nothing bad happens. We don't divide by 0. But we need to maintain equivalency to the original one. So we're just going to put in the domain restriction, h does not equal 0. We also had the original one, x does not equal 0, but we can still see that. If the x were 0 here, that would be a problem. And x plus h squared does not equal 0, which we split up like this. But yeah, so we box it off, and we're happy, and we call it a worksheet. So if you were to summarize this up and think about things, we did some work with fractions, we did some multiplication, expansion, distributing. That's all good. I think some good things to think about if you want some key comprehension questions. How do you know when you can cancel something from the numerator and the denominator? Okay, I think that's key idea 1 from this. Key idea 2 is, I mean, this is a simpler one, but how do you choose a foo? Okay. How do you choose a form of 1 to get a common denominator? Common denominator. Big idea number 3, I think, is how can you deal with fractions within fractions? Okay, so how do we turn those into a single fractional expression? So maybe I'll change this. How do you simplify fractions in fractions or turn into a single fraction or numerator denominator? Okay, that's a really key skill. Okay, another key skill is knowing binomial expansion. I mean, Pascal's triangle is really helpful. But really the most important one is the square of a binomial. So a plus b squared equals a squared plus 2ab plus b squared. I mean, that's just going to save you a ton of time. And the last one is, how do you know if / what to write as a domain restriction when simplifying rational expressions. Okay, so these are the big key questions when you do this worksheet. If you feel confident that you can A, do these things, and then B, if you can take all these key ideas and you say, I know all that, I've mastered this information, I fully understand each of these things, then you're in a good place. And if not, you just need more practice, come ask questions. You will get this, but those are the 5 things that I think are really important and that this worksheet is designed to make sure that you know, are fluent with, and are practiced and feel good about. So thanks for watching. Shoot this a like if you liked it. And if you disliked it, please do not dislike. That hurts my feelings. And have a great day.